Picture this, a golden orb suspended in the vast expanse of space, its light bathing our world in warmth and life. This is the sun, our closest star, and the unsung hero of our existence. For billions of years, it has been the silent guardian of our solar system, its glow a constant reminder of the delicate balance that keeps us alive. But have you ever stopped to think about the secrets it holds, the mysteries that lie hidden within its fiery core? Tonight, we embark on a journey to uncover the untold stories of our star, from its birth in a swirling cloud of gas and dust to the cosmic forces that shape its very being. As we drift through the wonders of space, let the soothing rhythm of this story guide you into a peaceful state of mind. So, wherever you are in the world, whether it's morning, noon, or night, let's take a moment to marvel at the sun's hidden mysteries together. What's the time where you are right now? Let us know in the comments. Now, close your eyes and let the story of our star unfold. Now, let's step back in time, way back, to the very beginning, when the sun was nothing more than a dream hidden in the depths of space. Around 4.6 billion years ago, a sprawling cloud of gas and dust, known as a nebula, began to collapse under its own gravity. This was no ordinary event. It was the spark that would ignite the birth of our star. Picture this vast, swirling cloud, dark and dense, slowly coming together, piece by piece, as if the universe itself were gathering its materials for something extraordinary. At the heart of this collapsing cloud, the temperature and pressure began to rise dramatically. As the material compacted tighter and tighter, the core grew hotter until it reached a staggering 15 million degrees Celsius. It was at this point that something incredible happened. Nuclear fusion ignited. Hydrogen atoms, the simplest and most abundant element in the universe, began to merge together, forming helium. This process released an immense amount of energy, and just like that, the sun was born, a fiery, glowing beacon of light. This newborn star became the heart of our solar system, its gravity pulling in the remaining gas and dust, shaping the planets, moons, and other celestial bodies that would orbit it. It's almost poetic, isn't it? The sun didn't just appear. It was forged through a cosmic alchemy of gravity, heat, and time. And now, billions of years later, it continues to shine, a testament to the power and beauty of the universe's creation. So, as we marvel at the sun's light today, let's remember the incredible journey it took to become the star that keeps our world alive. Moving deeper into the sun's story, let's take a journey through its layers, a fascinating tour from the heart of the star to its outer edges. At the very center lies the core, where temperatures soar to an astonishing 15 million degrees Celsius. Here, nuclear fusion transforms hydrogen into helium, releasing the energy that powers the sun, and by extension, our entire solar system. This process is the engine that keeps the sun burning bright, a cosmic furnace working tirelessly at its core. Surrounding the core is the radiative zone, a dense layer where energy travels outward, not through motion, but through the slow journey of photons. Imagine this energy bouncing around, taking thousands of years to move from the core to the next layer. It's a patient, deliberate dance that ensures the sun's energy eventually reaches its surface. Next comes the convective zone, where the energy transfer becomes more dynamic. Here, Hot plasma rises to the surface, cools, and then sinks back down, creating a churning, boiling motion. Picture a pot of water on the stove, bubbling and circulating as it heats up. That's the convective zone, a turbulent yet essential part of the sun's structure. As we move outward, we reach the photosphere, the sun's visible surface. This is the layer we see when we look up at the sun, shimmering with light and heat. It's here that sunspots appear, cooler, darker regions caused by intense magnetic activity. These blemishes on the sun's face remind us that even our star has its own unique features and quirks. Above the photosphere lies the chromosphere, a thin layer that glows with a reddish hue during solar eclipses. This layer is home to solar flares and prominences, dramatic bursts of energy that highlight the sun's constant activity. It's a place of both beauty and power, where the sun's energy manifests in stunning displays. Finally, we reach the corona, the sun's outermost layer, and perhaps its most mysterious. Despite being farther from the core, the corona is incredibly hot, reaching temperatures in the millions of degrees. This ethereal layer extends far into space, forming the solar wind that shapes the heliosphere and influences the entire solar system. Each layer of the sun plays a crucial role in its function and the energy it provides. Together, they create the dynamic, ever-changing star that sustains life on Earth. As we continue our exploration, we'll dive even deeper into the sun's secrets, uncovering more about this incredible celestial body that lights up our skies. Now let's zoom in on the sun's core, the powerhouse of our star. This is where the magic happens: nuclear fusion, the process that fuels the sun and keeps it shining. At the core, temperatures reach an incredible 15 million degrees Celsius, and pressures are millions of times greater than what we experience on Earth. These extreme conditions force hydrogen atoms to collide and fuse together, creating helium in the process. Every second, millions of tons of hydrogen are transformed into helium, releasing vast amounts of energy in the form of light and heat. This energy is the lifeblood of the sun, and it's what allows the star to radiate light and warmth across the solar system. Without nuclear fusion, the sun would simply fade away. The core's intense heat and pressure are the perfect environment for this reaction to occur. It's a delicate balance: too much pressure, and the sun would collapse; too little, and the fusion would stop. The core's role is not just to produce energy, but also to sustain the sun's structure. The energy generated here travels outward, first through the radiative zone, and then through the convective zone, eventually reaching the surface and beyond. This constant flow of energy ensures that the sun remains stable and continues to support life on Earth. Nuclear fusion is not unique to the sun. It's the same process that powers other stars in the universe. But for us, it's deeply personal. The sun's core is the source of the light that wakes us up in the morning, the heat that warms our planet, and the energy that drives weather systems and ecosystems. It's a reminder of how interconnected we are with the cosmos. As we continue to study the sun, scientists are working to understand even more about the core's behavior and the conditions that make nuclear fusion possible. Each discovery brings us closer to unlocking the secrets of our star and appreciating the incredible forces at work deep within its heart. Now, as we move outward from the sun's core, we enter the radiative zone, a region where energy takes on a slower, more deliberate pace. This layer stretches outward from the core for about 300,000 kilometers, and it's here that the energy produced by nuclear fusion begins its journey to the surface. But unlike the core, where energy is generated in a fiery frenzy, the radiative zone is a place of patience and persistence. In this dense and tightly packed layer, energy travels not as heat or light, but as photons, tiny particles of light. These photons bounce endlessly from one atom to another, zigzagging through the thick soup of plasma. It's a bit like a crowded room where everyone is trying to move at once, but no one can go very far without bumping into someone else. Because of this constant back and forth, a single photon can take thousands of years to escape the radiative zone and move outward. The reason for this slow dance is the incredible density of the radiative zone. The plasma here is so tightly packed that photons are absorbed and re-emitted countless times before they can finally break free. It's a process that requires immense time and energy, but it's also essential. It ensures that the energy generated in the core is distributed evenly throughout the sun. Interestingly, this process of energy transfer through photons is what makes the radiative zone so different from the layers above it. While the core is all about intense heat and pressure, the radiative zone is about endurance and stability. It's a critical bridge between the sun's fiery heart and its turbulent outer layers, ensuring that energy flows smoothly and consistently. As we'll see next, this energy eventually reaches the convective zone, where it takes on a much faster and more dynamic form. But for now, the radiative zone reminds us that even in the sun, not everything happens in a flash. Sometimes, the universe works in ways that are slow, steady, and utterly fascinating. As we venture further from the sun's core and through the enduring journey of the radiative zone, we arrive at the convective zone, a realm of motion and turbulence. This layer, extending from the radiative zone to the sun's surface, is where energy takes on a more dynamic and chaotic form. Imagine a pot of boiling water on a stove, where hot water rises to the surface, cools, and then sinks back down. Only here, the process happens on a cosmic scale with plasma, the sun's electrified gas. In the convective zone, the energy that has traveled so patiently through the radiative zone finally finds a faster way to move. Hot plasma rises from the depths, carrying heat upward, while cooler plasma sinks back down to be reheated and rise again. This constant churning motion creates a bubbling, boiling effect, driving energy toward the sun's surface with remarkable speed. It's a stark contrast to the slow, methodical pace of the radiative zone, reminding us that the sun's layers are as diverse as they are interconnected. The convective zone's turbulence is also responsible for some of the sun's most fascinating features, like granulation. When we look closely at the sun's surface, we can see a pattern of small, bright cells surrounded by darker edges. These are the tops of the convection currents, where hot plasma reaches the surface, cools, and sinks back down. It's a visual reminder of the sun's constant energy exchange, a process that keeps our star alive and vibrant. This boiling, bubbling layer plays a crucial role in the sun's overall structure and function. It's the final step in the journey of energy from the core to the surface, transforming the sun's inner heat into the light and warmth we experience on Earth. As we'll see next, this energy eventually reaches the photosphere, the sun's visible surface, where it takes on the form of sunlight. But for now, the convective zone reminds us that even in the vastness of space, motion and change are constants, driving the universe's endless dance. Now, as we move closer to the sun's outermost layers, we encounter the photosphere, the shimmering surface that defines the sun's appearance to us on Earth. This is the layer from which sunlight finally escapes into space, illuminating our planet and filling our skies with warmth and brightness. The photosphere is often referred to as the sun's surface, even though it's not solid like the ground beneath our feet. Instead, it's a thin layer of gas, only about 300 miles deep, where light is finally free to travel outward into the cosmos. One of the most striking features of the photosphere is its granulated texture. When observed closely, the sun's surface appears covered in tiny, bright cells surrounded by darker borders. These granules are the tops of the convection currents we explored earlier, where hot plasma rises to the surface, cools, and sinks back down. Each granule is about the size of a small country, and together they create a vibrant, ever-changing mosaic that showcases the sun's dynamic energy flow. But the photosphere is also home to darker, more mysterious features, sunspots. These are cooler, less active regions on the sun's surface, created by intense magnetic activity that inhibits the flow of heat. Sunspots often appear in pairs or groups and can grow to be many times larger than Earth. They're temporary, lasting anywhere from a few days to several weeks, but their presence is a key indicator of the sun's magnetic cycles. Over an 11-year period, the number of sunspots rises and falls, marking the solar maximum and minimum phases of the sun's activity. When we gaze at the sun from Earth, it's the photosphere we see, though its brightness makes it impossible to look at directly without proper protection. The light that reaches us from this layer takes just over 8 minutes to travel the 93 million miles between the sun and our planet. It's this light that powers photosynthesis in plants, warms our atmosphere, and sustains life as we know it. Yet, the photosphere is more than just a source of light and heat. It's a window into the sun's inner workings, revealing the intricate processes that drive our star's energy. From the dance of granules to the ebb and flow of sunspots, the photosphere offers a glimpse into the sun's dynamic and ever-changing nature. As we continue our journey, we'll explore the layers beyond the photosphere, where the sun's atmosphere reveals even more of its hidden mysteries. Now let's ascend beyond the photosphere and into the chromosphere, a layer of fire that adds a breathtaking crimson hue to the sun's atmosphere. This region, often nicknamed the sphere of color, becomes most visible during a total solar eclipse, when the moon blocks the sun's intense light, revealing a thin, reddish rim surrounding the darkened disk. This glow is caused by the presence of hydrogen gas, which emits a deep red light as it interacts with the sun's energy. The chromosphere is a turbulent and dynamic layer, spanning several thousand miles above the photosphere. Unlike the cooler regions of the sun's surface, the chromosphere grows hotter with altitude, reaching temperatures of up to 36,000 degrees Fahrenheit. This increase in heat is one of the sun's great mysteries, as the mechanisms behind this temperature rise are still not fully understood. This fiery layer plays a crucial role in solar activity, particularly in the formation of solar flares and prominences. Solar flares are sudden, intense bursts of energy that erupt from the sun's surface, often originating in the chromosphere. These explosions can release as much energy as 1 billion hydrogen bombs in just a few minutes, sending shockwaves of radiation and charged particles into space. When these particles reach Earth, they can disrupt satellites, interfere with communication systems, and even create stunning auroras in the polar skies. Prominences, on the other hand, are massive loops of plasma that extend far out from the sun's surface, sometimes reaching hundreds of thousands of miles into space. These structures are anchored by the sun's magnetic field and often form in the chromosphere before stretching into the corona. Prominences can last for days or even weeks, and when they collapse, they can trigger coronal mass ejections, huge clouds of solar material that travel through the solar system. The chromosphere is more than just a colorful spectacle. It's a vital part of the sun's dynamic behavior, connecting the surface to the outer atmosphere. Its role in solar flares and prominences highlights the intricate interplay between the sun's magnetic fields and its plasma, shaping the space weather that impacts our planet. As we move further outward, we'll explore the sun's outermost layer, the corona, a realm of even greater mystery and wonder. But for now, the chromosphere stands as a vivid reminder of the sun's fiery nature and its profound influence on the solar system. As we leave the fiery chromosphere behind, we step into one of the sun's most enigmatic realms, the corona. This outer atmosphere, often referred to as the sun's mystical crown, is a place of extreme temperatures and breathtaking beauty. Unlike the layers beneath it, the corona can reach temperatures of up to 3 million degrees Fahrenheit, far hotter than the sun's surface. This phenomenon, known as the coronal heating problem, remains one of the greatest mysteries in solar science, as researchers continue to explore what drives this incredible heat. The corona is also the birthplace of the solar wind, a constant stream of charged particles that flows from the sun and travels across the solar system. This cosmic breeze carries the sun's magnetic influence to the farthest reaches of the heliosphere, shaping the environment around planets and even affecting space, weather here on Earth. When the solar wind interacts with Earth's magnetosphere, it can create stunning auroras, painting the night sky with swirling colors of green, red, and purple. One of the most awe-inspiring features of the corona is its intricate web of coronal loops, huge, arching structures of plasma that trace the sun's magnetic field lines. These loops can stretch for hundreds of thousands of miles, glowing brightly in the extreme heat. They are often seen during solar eclipses or through specialized telescopes, offering a glimpse into the dynamic forces at work in the sun's outer atmosphere. The corona's beauty and mystery remind us how much we have yet to learn about our nearest star. As we continue our journey, we'll explore how these outer layers influence the entire solar system and beyond, revealing the sun's hidden secrets in even greater detail. Now, let's turn our attention to one of the sun's most dramatic displays, solar flares. These explosive bursts of energy are among the most powerful events in our solar system, releasing the equivalent of millions of nuclear bombs in a matter of minutes. Solar flares occur when the sun's magnetic field lines become twisted and suddenly snap, releasing an immense amount of energy across the electromagnetic spectrum, from radio waves to X-rays. The causes of solar flares are deeply rooted in the sun's complex magnetic activity. As the sun's magnetic fields twist and interact, they create intense regions of energy buildup. When the tension becomes too great, the field lines reconnect, unleashing a massive burst of radiation and charged particles. This process, known as magnetic reconnection, is the driving force behind these spectacular eruptions. The power of solar flares is staggering. A single flare can release energy equivalent to billions of megatons of TNT, dwarfing even the most powerful human-made explosions. But their effects extend far beyond their sheer intensity. When these bursts of energy reach Earth, they can interact with our planet's magnetosphere, causing geomagnetic storms that disrupt satellites, GPS systems, and even power grids. During particularly strong flares, communication systems can experience interference, and astronauts in space may need to seek shelter to avoid harmful radiation exposure. Perhaps one of the most awe-inspiring effects of solar flares is their role in creating auroras. When the charged particles from a flare collide with Earth's atmosphere, they energize the gases, producing the mesmerizing light displays known as the northern and southern lights. While these auroras are a beautiful reminder of the sun's influence, they also highlight the potential risks of solar activity to our increasingly technology-dependent world. Understanding solar flares is essential not only for protecting our infrastructure, but also for unraveling the sun's mysteries. As we continue to study these explosive events, we gain deeper insights into the sun's magnetic behavior and its far-reaching impact on our solar system. Up next, we'll explore another fascinating feature of the sun's sunspots and their connection to solar activity. Turning our gaze to the sun's surface, we encounter a fascinating phenomenon: sunspots. These dark patches, often visible through telescopes, are cooler regions on the sun's surface, created by intense magnetic activity. While they may appear small from our vantage point, sunspots can be vast, sometimes exceeding the size of Earth itself. But what makes them truly intriguing is their connection to the sun's magnetic behavior and their role in shaping solar activity. The formation of sunspots begins with the sun's magnetic field. When magnetic lines become particularly strong, they inhibit the flow of heat from the sun's interior to its surface, creating cooler areas that appear darker compared to their surroundings. These magnetic knots can persist for days, weeks, or even longer, forming the distinctive spots we observe. Despite their lower temperatures, sunspots are still incredibly hot, reaching thousands of degrees Celsius. One of the most remarkable aspects of sunspots is their cyclical nature. Approximately every 11 years, the sun goes through what's known as the solar cycle, during which the number of sunspots fluctuates dramatically. At the peak of the cycle, known as solar maximum, the the sun's surface is dotted with numerous sunspots, while at solar minimum, they become rare or even disappear entirely. This cycle is driven by the sun's magnetic field, which gradually flips polarity over time, creating a rhythm of activity that scientists have been studying for centuries. Historically, sunspots have captured human curiosity for millennia. Ancient astronomers in China recorded observations of these dark marks as early as several hundred years BC, and Galileo Galilei's detailed studies in the 17th century marked a turning point in our understanding of the sun. Today, modern telescopes and satellites allow us to monitor sunspots with unprecedented precision, revealing their intricate structures and behaviors. But sunspots are more than just a historical curiosity. They play a key role in solar storms. These dark regions are often the breeding grounds for solar flares and coronal mass ejections, as the twisted magnetic fields they harbor can suddenly release vast amounts of energy. When such events occur, the effects ripple across the solar system, potentially impacting Earth's magnetic field and technological systems. By studying sunspots, we gain valuable insights into the sun's magnetic dynamics and its influence on space weather. As we continue to unravel their mysteries, these dark secrets of the sun remind us of the intricate and powerful forces at play in our cosmic neighborhood. Next, we'll journey into the realm of solar prominences, where fiery arcs of plasma stretch across the sun's surface, showcasing yet another mesmerizing aspect of our star. As we now turn our attention to another captivating feature of the sun, let's explore the breathtaking phenomenon of solar prominences. These immense arcs of glowing plasma stretch thousands of kilometers above the sun's surface, creating a spectacle that is both beautiful and powerful. Picture vast ribbons of fire arching gracefully through space, held in place by the sun's magnetic forces. Solar prominences form when dense concentrations of plasma are trapped within the sun's magnetic field. These magnetic loops act like invisible highways, guiding the plasma into towering structures that can persist for days or even weeks. Despite their fiery appearance, prominences are cooler and denser than the surrounding corona, which is why they stand out so vividly against the sun's outer atmosphere. One of the most striking aspects of solar prominences is their sheer scale. Some of these loops can stretch farther than the distance from Earth to the Moon, making them among the largest structures in our solar system. Their size and stability are a testament to the complex interplay between the sun's magnetic field and its superheated plasma. Prominences are not just static features, they are dynamic and ever-changing. Over time, they can twist, erupt, or even break away from the sun's surface in spectacular events, known as solar flares or coronal mass ejections. When this happens, the energy released can send torrents of charged particles streaming into space, sometimes reaching Earth and interacting with our planet's magnetosphere. The connection between prominences and solar activity makes them a key area of study for scientists. By observing these fiery arcs, researchers can gain insights into the sun's magnetic behavior and its influence on space weather. Understanding prominences helps us predict solar storms, which can impact satellites, communication systems, and even power grids on Earth. As we marvel at these loops of plasma, we are reminded of the sun's immense power and the intricate forces that shape its behavior. Solar prominences are not just a visual wonder, they are a window into the dynamic heart of our star. Next, we'll take a closer look at the solar wind, a constant stream of particles flowing from the sun that shapes the very fabric of our solar system. Moving deeper into the sun's influence, let's explore the solar wind, a constant flow of charged particles that streams outward from our star. This invisible breeze, made up of electrons, protons, and other particles, travels at incredible speeds, reaching every corner of the solar system. It's a fundamental force that shapes the space around us, creating a protective bubble known as the heliosphere. The solar wind originates in the sun's corona, its outermost layer. Here, the intense heat energizes particles to the point where they can escape the sun's gravity and stream into space. This flow isn't uniform. It varies in speed and density depending on the sun's activity, from gentle streams to powerful gusts during solar storms. These variations are driven by the sun's magnetic field, which plays a crucial role in directing and accelerating the particles. As the solar wind expands outward, it carves out the heliosphere, a vast region that acts as a shield for the solar system. The heliosphere extends far beyond the orbit of Pluto, protecting planets from the harsh cosmic radiation that fills interstellar space. It's like an invisible cocoon, with the solar wind acting as the threads that weave it together. Without this protective barrier, life on Earth would face greater challenges from high-energy particles zipping through the galaxy. When the solar wind reaches Earth, it interacts with our planet's magnetosphere, the magnetic field that surrounds us. This interaction can produce stunning natural phenomena, such as the auroras, when charged particles from the solar wind collide with gases in Earth's atmosphere. They create glowing curtains of light in the polar skies, a breathtaking reminder of the sun's influence. However, intense solar wind can also disrupt our technology, affecting satellites, communication systems, and even power grids on the ground. Understanding the solar wind is essential for space exploration and safeguarding our modern infrastructure. By studying its behavior, scientists can predict space weather and mitigate its effects on technology. It's a testament to how connected we are to the sun, even from millions of kilometers away. Next, we'll journey to the outer edges of the sun's influence and discover the heliosphere, the vast bubble that defines the boundaries of our solar system. As we venture further into the sun's realm, we encounter the heliosphere, an immense bubble that defines the extent of the sun's influence. This vast region of space is shaped by the solar wind, a continuous outflow of charged particles streaming from the sun's corona. Stretching far beyond the orbit of Pluto, the heliosphere acts as a protective shield for our solar system, safeguarding planets and other celestial bodies from the relentless onslaught of cosmic radiation that fills the void of interstellar space. The heliosphere isn't just a static boundary, it's a dynamic structure, constantly shaped by the interplay between the sun's solar wind and the pressure of interstellar particles. Imagine it as a cosmic force field, with the solar wind pushing outward and the interstellar medium pressing inward. The point where these forces meet is called the heliopause, the outer edge of the heliosphere. Beyond this boundary lies the uncharted territory of interstellar space, where the sun's influence fades and the galaxy takes over. This protective bubble plays a crucial role in preserving the delicate balance of life on Earth. Without the heliosphere, high-energy cosmic rays from distant supernova and other cosmic events would flood our solar system, bombarding planets with harmful radiation. These particles could disrupt the atmospheres of planets, damage DNA, and make life, as we know it, far more challenging to sustain. The heliosphere's ability to deflect much of this radiation is one of the reasons our solar system remains a relatively safe haven in the vastness of space. The shape and size of the heliosphere are influenced by the Sun's motion through the galaxy. As the Sun moves, it creates a sort of cosmic wake, with the heliosphere stretching out behind it like a comet's tail. This movement also means the heliosphere isn't perfectly spherical. It's more like a teardrop, with a rounded front and an elongated tail extending in the opposite direction of the Sun's path. Studying the heliosphere helps us understand not only our own solar system, but also the broader interactions between stars and the interstellar medium. Missions like Voyager 1 and 2 have provided invaluable data by crossing the heliopause and sending back information from the edge of the Sun's influence. These explorations reveal how the heliosphere interacts with the galaxy, offering insights into the protective mechanisms that allow life to thrive in our corner of the universe. As we continue to explore the mysteries of the Sun, the heliosphere serves as a reminder of our star's far-reaching impact. It's a testament to how the Sun's energy and influence extend far beyond the planets, shaping the very boundaries of our cosmic neighborhood. Next, we'll dive into the Sun's magnetic field, a powerful force that drives much of the activity we see on and around our star. Shifting our focus to another aspect of the Sun's influence, we encounter its magnetic field, a cosmic force that shapes much of the activity we observe on and around our star. The Sun's magnetic field is not static. It's a dynamic, ever-changing web of energy that permeates every layer of the Sun and extends far into space. This magnetic field is generated by the movement of charged particles within the Sun's interior, particularly in the convective zone, where swirling plasma creates electric currents. These currents, in turn, produce magnetic fields that twist, loop, and interact in complex ways. The Sun's magnetic field undergoes a regular cycle known as the solar cycle, which lasts approximately 11 years. During this cycle, the magnetic field flips, with the north and south poles swapping places. This cycle is closely tied to solar activity, including the formation of sunspots, solar flares, and coronal mass ejections. At the peak of the solar cycle, known as solar maximum, the Sun's magnetic field is at its most chaotic, leading to increased sunspots and frequent solar storms. Conversely, during solar minimum, the magnetic field becomes more stable and solar activity diminishes. Sunspots are one of the most visible manifestations of the Sun's magnetic field. These dark, cooler regions on the Sun's surface are caused by intense magnetic activity that inhibits the flow of heat from the interior. Sunspots often appear in pairs or groups, with each pair representing the points where magnetic field lines emerge from and re-enter the Sun's surface. The number of sunspots rises and falls in tandem with the solar cycle, providing astronomers with a way to track the Sun's magnetic activity. Solar flares, on the other hand, are sudden, explosive releases of energy that occur when the sun's magnetic field lines become twisted and snap. These powerful bursts of radiation can heat the sun's atmosphere to millions of degrees and send charged particles speeding across the solar system. When directed toward Earth, solar flares can disrupt communications, damage satellites, and even create stunning auroras in the polar regions. Similarly, coronal mass ejections, massive eruptions of plasma and magnetic field from the sun's corona, are driven by the sun's magnetic field and can have significant effects on space weather. The sun's magnetic field also extends far beyond its surface, shaping the solar wind and influencing the heliosphere. As the solar wind carries the sun's magnetic field into space, it creates a vast interplanetary magnetic field that interacts with the magnetic fields of planets and other celestial bodies. This interplanetary magnetic field plays a crucial role in protecting Earth from harmful cosmic radiation by deflecting charged particles away from our planet. Understanding the sun's magnetic field is key to unlocking many of the mysteries surrounding our star. It drives the processes that produce solar flares, sunspots, and the solar wind, while also playing a vital role in protecting our solar system from cosmic dangers. As we continue to study this cosmic force, we gain deeper insights into the dynamic nature of the sun and its far-reaching influence on the universe. Now, let's turn our attention to one of the most breathtaking phenomena influenced by the sun and the moon, the solar eclipse. This celestial event occurs when the moon moves between the Earth and the sun, casting a shadow on our planet and temporarily blocking the sun's light. The result is a mesmerizing display of nature, where day briefly turns to night and the sun's corona becomes visible in all its ethereal glory. Solar eclipses come in three main types: total, partial, and annular. During a total solar eclipse, the moon completely covers the sun, plunging the area within its shadow, known as the path of totality, into darkness. This is the most dramatic type, offering viewers a rare glimpse of the sun's outer atmosphere, the corona, which is usually hidden by the sun's intense brightness. A partial solar eclipse happens when only a portion of the sun is obscured by the moon, creating a crescent-shaped sun in the sky. An annular eclipse occurs when the moon is farther from Earth in its orbit, making it appear slightly smaller than the sun. This creates a ring of fire effect, where the sun's edges remain visible around the moon. The rarity of solar eclipses adds to their allure. While solar eclipses occur somewhere on Earth about every 18 months, witnessing a total solar eclipse from any specific location is much less frequent, often happening only once every few centuries. This rarity makes them highly anticipated events, drawing observers from around the world to experience the fleeting moments of this cosmic alignment. The science behind solar eclipses is rooted in the precise alignment of the sun, moon, and Earth. The moon's orbit around Earth is tilted slightly relative to Earth's orbit around the sun, which is why eclipses don't happen every month. When these orbits align correctly, the moon's shadow falls on Earth, creating an eclipse. The moon's distance from Earth also plays a role, influencing whether an eclipse is total, partial, or annular. Solar eclipses have captivated humans for millennia, inspiring awe, fear, and scientific curiosity. Ancient cultures often interpreted them as omens or messages from the gods, while modern science uses them as opportunities to study the sun's corona and other phenomena that are normally hidden from view. Today, eclipses continue to unite people in wonder, reminding us of the intricate dance of celestial bodies that shapes our universe. As we marvel at the beauty of a solar eclipse, let's remember that it's not just a visual spectacle, it's a testament to the precise and delicate balance of our solar system. This cosmic alignment offers us a fleeting moment to reflect on the wonders of the universe and our place within it. Now, let's shift our focus to the sun's pivotal role in our solar system. As the heart of this cosmic neighborhood, the sun's influence is both vast and essential. Its most immediate gift to us is energy. Every ray of sunlight that reaches Earth fuels life itself, driving photosynthesis in plants, which in turn supports the entire food chain. Without the sun's warmth and light, life as we know it simply wouldn't exist. But the sun's role extends far beyond providing energy. Its immense gravitational pull acts as the anchor for our solar system, keeping planets, moons, and other celestial bodies in their orbits. This gravitational force ensures the stability and harmony of our cosmic dance. For instance, Earth's steady orbit around the sun allows for the consistent seasons and climates that make life possible. The sun also shapes space weather, a phenomenon that affects not only Earth, but the entire solar system. Solar winds, streams of charged particles emitted by the sun, interact with planetary magnetic fields, creating stunning displays like the auroras. However, these winds can also disrupt satellite communications and power grids on Earth, highlighting the sun's dual nature as both a giver and a disruptor. Through its energy, gravity, and solar activity, the sun governs the rhythm of our solar system. It's a reminder of how interconnected everything is, from the tiniest plant on Earth to the farthest reaches of space. As we continue to explore the mysteries of the sun, we gain a deeper understanding of its indispensable role in the grand tapestry of the universe. Now, let's turn our attention to the sun's profound influence on Earth's climate. As the ultimate source of energy for our planet, the sun's rays are the driving force behind Earth's weather patterns and climate systems. When sunlight reaches Earth, it warms the surface, creating temperature differences that power wind currents, ocean currents, and the water cycle. These processes are the backbone of the weather we experience every day, from gentle breezes to powerful storms. But the sun's impact on climate goes beyond day-to-day weather. Over longer periods, variations in the sun's energy output can influence global temperatures. One such variation is the solar cycle, an approximately 11-year pattern of fluctuating solar activity. During periods of high activity, the sun emits more energy, which can contribute to slightly warmer global temperatures. Conversely, during quieter phases, Earth may experience a cooling effect. Interestingly, historical records show that extended periods of reduced solar activity, such as the Maunder minimum in the late 17th century, coincided with cooler global temperatures, often referred to as mini ice ages. While the sun's cycles are just one piece of the complex climate puzzle, they highlight the intricate connection between our star and Earth's environment. Understanding the sun's role in shaping Earth's climate not only deepens our appreciation for its power, but also underscores the delicate balance that sustains life on our planet. As we continue to study these interactions, we gain valuable insights into the natural processes that shape our world. Now, as we shift our gaze to the broader cosmic journey of the Sun, let's explore its life cycle, a story of transformation spanning billions of years. Right now, the Sun is in the prime of its life, a phase known as the main sequence. Here, it steadily burns hydrogen into helium through nuclear fusion, providing the energy that lights up our solar system. This stable stage has been ongoing for around 4.6 billion years and will continue for roughly another 5 billion years. But like all stars, the Sun's story doesn't end here. As its hydrogen fuel gradually depletes, the Sun will enter a new chapter. In about 5 billion years, it will begin to evolve into a red giant. During this phase, the Sun's core will shrink, while its outer layers expand dramatically, engulfing nearby planets, including possibly Earth. This expansion will mark a dramatic shift in the Sun's appearance and behavior as it becomes a cooler yet vastly larger star. Eventually, the Sun will shed its outer layers, creating a glowing shell of gas known as a planetary nebula. What remains will be its core, now a dense and intensely hot remnant called a white dwarf. Over trillions of years, this white dwarf will cool and fade, becoming a dim and silent relic of the Sun's once fiery existence. This life cycle, from birth to death, is a universal process shared by countless stars across the universe. Understanding the Sun's journey not only deepens our connection to it, but also reminds us of the dynamic and ever-changing nature of the cosmos. Next, we'll explore how this life cycle connects to the broader mysteries of the universe and what it means for the future of our solar system. Now, let's turn our attention to the Sun's most profound gift to us: energy. It's this energy that makes life on Earth possible. Every beam of sunlight that reaches our planet fuels the process of photosynthesis in plants, turning carbon dioxide and water into the oxygen we breathe and the food we eat. This intricate dance of light and life forms the foundation of Earth's ecosystems, supporting everything from the tiniest microorganisms to the largest animals. But the Sun's energy doesn't stop there. It warms our planet, creating the conditions necessary for water to exist in its liquid form, a critical ingredient for life as we know it. Without the Sun's steady heat, Earth would be a frozen, lifeless world. Its light also regulates our climate, driving weather patterns and seasons that shape the rhythm of life across the globe. Beyond Earth, the Sun's energy plays a role in the broader universe. It illuminates our solar system, allowing us to observe and study distant worlds. Its gravitational pull keeps planets in their orbits, maintaining the delicate balance that makes our cosmic neighborhood so unique. In a sense, the Sun is not just a star, it's a beacon of life, a reminder of how interconnected we are with the cosmos. As we reflect on the Sun's energy, it's hard not to feel a sense of awe. This giant ball of gas, burning millions of miles away, is the reason we're here. It's a testament to the power of the universe to create and sustain life, and a reminder of our place in this vast, intricate web of existence. Next, we'll explore how ancient civilizations revered the Sun, weaving it into their myths and cultures as a symbol of life and divinity. Turning our gaze back through time, we find that the sun has long held a sacred place in the hearts and minds of humanity. Ancient civilizations across the globe revered the sun, seeing it as more than just a source of light and warmth. It was a symbol of life, power, and divinity. For them, the sun wasn't just a star, it was a god, a guide, and a central figure in their understanding of the world. In Egypt, the sun god Ra was one of the most important deities, believed to travel across the sky each day in a chariot, bringing light and life to the land. The pyramids, monumental structures that have stood the test of time, were aligned with the sun's movements, serving as both tombs and symbols of the pharaoh's connection to the divine. Similarly, in ancient Mesopotamia, the sun god Shamash was seen as a bringer of justice and truth, his rays illuminating the path of righteousness. Across the Atlantic, the Maya of Central America built their elaborate calendars around the sun's cycles, using it to mark the passage of time and plan agricultural activities. Their pyramids, like those in Egypt, were constructed to align with solar events, such as the equinoxes, when the sun would cast dramatic shadows that seemed to bring the structures to life. In the Andes, the Inca worshipped Inti, the sun god, believing he was the ancestor of their rulers and the source of their prosperity. The famous Inti Raymi festival, still celebrated today, honors the sun as the giver of life. Even in cultures that didn't personify the sun as a deity, its influence was undeniable. The ancient Greeks and Romans saw the sun as a symbol of order and rationality, with Apollo, the god of the sun, also representing music, poetry, and healing. Stonehenge, the mysterious stone circle in England, is thought to have been used as an ancient solar calendar, marking the solstices and connecting its builders to the rhythms of the cosmos. These ancient cultures, separated by vast distances in time, all shared a profound reverence for the sun. They built monuments, created rituals, and told stories that reflected their awe and gratitude for its life-giving power. In doing so, they wove the sun into the very fabric of their societies, leaving a legacy that continues to inspire us today. As we move forward, we'll see how modern science has deepened our understanding of this celestial wonder, unlocking new mysteries and marvels. Now, let's shift our focus to the present and explore how modern science has transformed our understanding of the sun. With the advent of advanced technology, we've been able to uncover secrets that were once beyond our reach, shedding new light on the mysteries of our closest star. Telescopes, both on Earth and in space, have become our eyes into the sun's fiery depths, revealing details that were unimaginable to ancient civilizations. One of the most significant tools in this quest for knowledge is the solar telescope, designed specifically to observe the sun. Instruments like the Daniel K. Inau, a solar telescope in Hawaii, capture incredibly detailed images of the sun's surface, allowing scientists to study sunspots, solar flares, and other phenomena with unprecedented clarity. These observations help us understand the sun's magnetic field and its role in driving solar activity. Space-based observatories have also revolutionized our understanding. Satellites like the Solar and Heliospheric Observatory, or SOHO, and the Parker Solar Probe have provided invaluable data, The Parker Solar Probe, in particular, has ventured closer to the Sun than any other spacecraft, braving extreme temperatures to measure the Sun's corona and solar wind. These missions have revealed insights into how the Sun's outer atmosphere heats to millions of degrees and how solar particles flow into space, affecting the entire solar system. Through these technologies, scientists have made groundbreaking discoveries. For instance, we've learned that the Sun's magnetic field is far more complex than previously thought, with magnetic loops and twists that can trigger solar storms. These storms, while awe-inspiring, can have real-world impacts on Earth, disrupting satellites, communication systems, and even power grids. Understanding these processes is crucial for predicting space, weather, and mitigating its effects. Ongoing research continues to push the boundaries of our knowledge. Projects like the European Space Agency's Solar Orbiter aim to study the Sun's poles, regions that have never been fully observed. By analyzing these areas, scientists hope to uncover clues about the Sun's magnetic cycles and how they influence solar activity over time. Every discovery brings us closer to understanding the Sun's inner workings and its profound influence on our solar system. Modern science has not only deepened our knowledge of the Sun, but also connected us to it in new ways. What was once a symbol of divinity is now a subject of rigorous study, a testament to humanity's relentless curiosity and ingenuity. As we continue to explore, the Sun remains a source of wonder, inspiring us to unlock its secrets and appreciate its role in the cosmos. As we look ahead, the Sun's future holds both wonder and transformation. In about 5 billion years, our closest star will enter a dramatic new phase of its life. The Sun, now a stable source of light and energy, will begin to exhaust its hydrogen fuel. As this happens, its core will contract while its outer layers expand, transforming it into a red giant. This colossal expansion will engulf the inner planets, including Mercury and Venus, and bring the Sun's fiery reach perilously close to Earth. During this phase, the Sun's surface will cool slightly, glowing with a reddish hue, but its immense size will dominate the solar system. Earth's fate remains uncertain. Some models suggest our planet might be pushed outward, escaping the Sun's grasp, while others predict it will be consumed by the expanding star. Regardless of the outcome, Earth's surface will become uninhabitable long before this event, as the Sun's increasing brightness will evaporate oceans and scorch the land. As the red giant phase continues, the Sun will shed its outer layers, creating a beautiful planetary nebula. This glowing shell of gas and dust will drift into space, leaving behind the Sun's core, which will collapse into a dense, Earth-sized remnant called a white dwarf. Over billions of years, this white dwarf will slowly cool and fade, marking the end of the Sun's active life. The broader implications for the solar system are profound. The outer planets, like Jupiter and Saturn, may survive, but their environments will be drastically altered. The Sun's expansion will heat their icy moons, potentially creating temporary habitable zones. Meanwhile, the solar system's structure will shift, with the remaining planets orbiting the fading white dwarf in a vastly different arrangement. This future, though distant, reminds us of the Sun's central role in shaping our solar system. It also highlights the impermanence of celestial bodies, even those as seemingly eternal as our sun. While we may never witness these events, they inspire us to cherish the sun's current stability and the life it sustains. As we continue to explore and understand our star, we gain not only knowledge, but also a deeper appreciation for the delicate balance that makes our existence possible. Next, let's explore how the sun's energy has influenced Earth's climate and weather patterns, shaping the environment we depend on every day. As we turn our attention to space exploration, the sun plays a pivotal role that extends far beyond its light and warmth. It is both a source of energy and a formidable challenge for spacecraft venturing into the cosmos. Solar panels, for instance, harness the sun's rays to power missions, from satellites orbiting Earth to rovers exploring distant planets like Mars. Without this abundant energy, many of our greatest space achievements would not be possible. Yet, the sun also presents significant hurdles for space travel. Its intense radiation can pose serious risks to both spacecraft and astronauts. Prolonged exposure to solar particles can damage sensitive electronics and pose health threats, such as increased cancer risk for crew members. Engineers and scientists must design protective shields and carefully plan mission trajectories to minimize these dangers, especially for journeys beyond Earth's protective magnetosphere. The sun's influence is particularly crucial in planning interplanetary travel. Its gravitational pull affects the paths of spacecraft, enabling maneuvers like gravity assists, which use a planet's orbit to slingshot a probe further into space. Missions to the outer planets, such as Voyager and Cassini, relied heavily on these techniques to conserve fuel and extend their reach. Solar activity also shapes the timing of space missions. Solar flares and coronal mass ejections can disrupt communication systems and navigation instruments, making it essential to monitor the sun's activity closely. Launch windows are often chosen during periods of relative solar calm to reduce risks and ensure smoother operations. Understanding the sun's behavior is critical for the future of space exploration, especially as we aim for ambitious goals like crewed missions to Mars and beyond. By studying solar phenomena, we can develop better technologies to protect astronauts and spacecraft, ensuring safer and more efficient journeys through the solar system. The sun's dual role as both a provider and a challenger underscores its importance in our quest to explore the universe. It reminds us that while the cosmos is vast and complex, our closest star remains at the heart of every mission, guiding us as we reach for the stars. Next, we'll uncover the unsolved mysteries of the sun, from the enigma of its scorching corona to the secrets of its magnetic fields. Stepping deeper into the sun's enigmatic nature, we encounter questions that continue to puzzle even the brightest minds in science. One of the most perplexing mysteries is the coronal heating problem. While the sun's surface, or photosphere, reaches temperatures of around 5,500 degrees Celsius, the corona, its outermost layer, soars to over 1 million degrees. How does the corona become so blisteringly hot, even though it's farther from the sun's core? Scientists have proposed various theories, from magnetic waves transferring energy to tiny, explosive events called nanoflares, but a definitive answer remains elusive. Another mystery lies in the sun's magnetic field. While we know that its dynamic magnetic activity drives phenomena like sunspots, solar flares, and prominences, the exact mechanisms behind these processes are still not fully understood. The sun's magnetic field is incredibly complex, constantly twisting, breaking, and reconnecting in ways that defy simple explanation. This magnetic chaos not only shapes the sun's behavior, but also impacts space weather, which can have profound effects on Earth and our technology. Adding to the intrigue, the sun's internal structure holds secrets of its own. For instance, how does the solar dynamo, the process that generates the sun's magnetic field, actually work, and what drives the sun's 11-year activity cycle, during which sunspots and solar flares wax and wane? These questions are at the forefront of solar research, with missions like NASA's Parker Solar Probe and ESA's Solar Orbiter gathering unprecedented data to help unlock the answers. Even the sun's quieter moments pose puzzles. Why do periods of low solar activity, known as solar minima, sometimes last longer than expected? And how do these quiet phases affect Earth's climate and atmosphere? These questions highlight the sun's intricate relationship with our planet and the broader solar system. As we continue to explore these mysteries, each discovery brings us closer to understanding not just our sun, but the countless stars that light up the universe. The sun's hidden questions remind us that even the most familiar objects in the sky still hold secrets waiting to be uncovered. Next, we'll marvel at the sun's breathtaking beauty, from its golden rays at sunrise to the stunning auroras it creates in our night sky. Shifting our gaze from the sun's scientific mysteries, let's take a moment to appreciate its breathtaking beauty. Every sunrise and sunset offers a celestial masterpiece, as the sun's golden rays paint the sky in hues of orange, pink, and gold. These moments, fleeting yet timeless, remind us of the sun's role as both a giver of life and a source of inspiration. The light that filters through the atmosphere creates a kaleidoscope of colors, transforming ordinary landscapes into scenes of extraordinary wonder. But the sun's artistry doesn't end with its daily rise and fall. During solar activity, it gifts us with the auroras, those ethereal lights that dance across the polar skies. When charged particles from the sun collide with Earth's atmosphere, they ignite vibrant curtains of green, purple, and blue, creating a spectacle that feels almost otherworldly. These shimmering displays, known as the Northern and Southern Lights, have captivated humans for centuries, inspiring myths, art, and a deep sense of awe. Even the sun's surface, when observed through specialized telescopes, reveals its own kind of beauty. The intricate patterns of sunspots, the graceful arcs of solar prominences, and the shimmering glow of the corona all contribute to a visual symphony that speaks to the sun's dynamic nature. Each feature tells a story of immense energy, magnetic forces, and cosmic processes that shape not just our star, but the entire solar system. The sun's beauty is a reminder of its dual nature, both a scientific marvel and a source of artistic inspiration. It invites us to look up, to wonder, and to appreciate the profound connection between the cosmic and the earthly. As we continue to explore its secrets, let's not forget to pause and marvel at the sheer visual splendor it brings to our world. Next, we'll delve into how the sun's influence has shaped human culture throughout history, from ancient myths to modern art. Turning from the sun's visual wonders, we find its influence woven deeply into the tapestry of human culture. For centuries, the sun has been more than just a celestial body. It has been a muse, a symbol, and a source of endless inspiration. In art, the sun often represents life, vitality, and divinity. From the golden rays in ancient Egyptian hieroglyphs to the radiant halos in Renaissance paintings, artists have used its light to convey power, hope, and transcendence. Music, too, has been shaped by the sun's presence. Think of songs that celebrate its warmth, from classical compositions like Vivaldi's Spring to modern anthems that evoke the joy of sunny days. The sun's rhythm mirrors the heartbeat of human creativity, inspiring melodies that resonate with both energy and calm. Literature is no exception. Poets and writers have long turned to the sun as a metaphor for enlightenment, love, and the passage of time. Shakespeare's sonnets often compare the beloved's beauty to the sun's brilliance, while authors like Ray Bradbury have used the sun as a central theme to explore human ambition and vulnerability. Even in mythology, the sun takes center stage, from the Greek god Helios driving his chariot across the sky to the Aztec deity Huitzilopochtli, who demanded sacrifices to ensure the sun's daily return. Beyond its artistic significance, the sun holds deep symbolic meaning across cultures. It represents renewal, as each sunrise brings the promise of a new day. It embodies resilience, shining through even the darkest storms, and it serves as a reminder of our connection to the cosmos, a celestial force that unites all life on Earth. As we reflect on the sun's role in human culture, we see how it has ignited creativity, shaped traditions, and fueled the human imagination. Its light continues to illuminate not just our skies, but also our stories, our songs, and our shared sense of wonder. Next, we'll explore how the sun fits into the broader galaxy as we uncover its cosmic neighbors and its place among the stars. Now let's shift our gaze beyond the sun and into the vast expanse of the Milky Way, where our star is just one among billions. Nestled in one of the galaxy's spiral arms, the sun is part of a stellar family that stretches across an unimaginable distance. The Milky Way itself is a swirling disk of stars, gas, and dust, spanning about 100,000 light years from end to end. Within this grand structure, the sun occupies a spot roughly 27,000 light years from the galactic center, orbiting slowly but steadily around it. Around the sun, countless other stars share this cosmic neighborhood. Some are similar in size and brightness, while others are vastly different, ranging from dim red dwarfs to luminous blue giants. Together, these stars form a tapestry of light, each contributing to the galaxy's intricate design. The sun's position in the Orion Arm, a minor spiral arm of the Milky Way, places it in a region rich with stellar activity and cosmic wonders. But the sun's role in the galaxy goes beyond simply being a resident. Its gravitational influence extends to the planets, moons, and other bodies in our solar system, holding them in a delicate balance. This influence also helps shape the structure of the heliosphere, a protective bubble that shields our solar system from the harsher elements of interstellar space. Beyond its immediate surroundings, the sun's light and energy travel outward, contributing to the galaxy's overall luminosity and warmth. In the grand scheme of the Milky Way, the sun is just one star among countless others, yet it plays a vital part in the galaxy's story. Its position, energy, and influence are threads in the larger cosmic fabric, reminding us of our place in the universe. As we continue our journey, we'll reflect on the sun's legacy, not just as a star, but as a symbol of connection and wonder in the vastness of space. Let us now pause for a moment to reflect on the sun's profound legacy within the universe. Though it may seem like just another star in the tapestry of the Milky Way, the sun holds a special place in the cosmos. It is the heart of our solar system, the source of life, giving energy for Earth, and the gravitational anchor that keeps planets and moons in their orbits. Without its steady glow, life as we know it would not exist, and the delicate balance of our solar system would unravel. Yet, when we zoom out to the scale of the galaxy, the sun becomes just one of billions of stars, each with its own story to tell. Some stars are older, some younger, some larger, and some smaller, but what makes our sun unique is its connection to us. It is our star, the one we orbit, the one we depend on, and the one that has shaped the course of our existence. The sun's legacy extends beyond its immediate influence. Its light travels across the vastness of space, carrying its energy to the farthest reaches of the galaxy. It is a reminder of our place in the cosmos, a testament to the beauty and complexity of the universe. While it may not be the brightest or the largest star, it is ours, a symbol of connection, warmth, and wonder. As we gaze at the sun, let us not just see a fiery ball of gas, but a beacon of life, and a reminder of the intricate web of existence that binds us to the stars. In its light, we find inspiration to explore, to learn, and to appreciate the marvels of the universe. The sun's legacy is not just its role in the cosmos, but its ability to ignite our curiosity and remind us of the infinite possibilities that lie beyond. As we bring our journey through the secrets of the sun to a close, let us take a moment to marvel at the wonders we've uncovered. From its fiery birth to its role as the life-giving heart of our solar system, the sun has revealed itself as a source of both mystery and inspiration. Its layers, its energy, and its influence on Earth remind us of the delicate balance that sustains life and the vastness of the cosmos we are part of. The sun's mysteries are not just scientific puzzles, but invitations to explore and understand our place in the universe. Its light, warmth, and energy have shaped not only our planet, but also our imagination, culture, and thirst for knowledge. Whether through the dance of solar flares, the beauty of sunsets, or the awe of a solar eclipse, the sun continues to captivate us, reminding us of the beauty and complexity of the natural world. As you reflect on the sun's legacy, let its light guide you toward curiosity and wonder. Tonight, as you close your eyes, imagine the sun's golden rays reaching across the cosmos, connecting you to the vastness of space and the infinite possibilities it holds. Let its warmth and brilliance fill you with a sense of peace and gratitude, knowing that we are all part of something much larger than ourselves. So, as you drift into a restful sleep, take a moment to appreciate the sun, our star, our source of life, and our gateway to the universe. Thank you for joining us on this journey through the secrets of the sun. If you enjoyed this exploration, don't forget to like, subscribe, and hit the notification bell for more cosmic adventures. Until next time, may the sun's light inspire your dreams and guide your curiosity. Sleep well and sweet dreams.